You know, the ground beneath our feet feels pretty solid, right? But it's actually just the thin skin of a really restless planet. So today, we're going to dive into this amazing scientific detective story that revealed what's really going on down there and how it totally changed our view of the world.
For like most of human history, the answer to that seemed pretty obvious. We live on a big solid ball of rock. But there were these stubborn little clues, like how much the Earth actually weighed, that just didn't add up. They hinted at a much more complex story.
Yeah, the simplest guess was that the Earth was just solid rock, all the way through. It's a sensible guess, right? Well, it turns out it was spectacularly wrong.
So the first big crack in that old idea showed up way back in the 1600s. Scientists like Isaac Newton did the math on Earth's density and found something strange. It was twice as heavy as the rocks on the surface could account for. That meant the inside had to be made of something way denser. This gave rise to the onion theory, the idea that our planet was made of distinct layers.
So, how do you see inside a planet? I mean, you can't just drill to the center. Well, the breakthrough came from a totally unexpected place: earthquakes. By studying the shockwaves they send ripping through the Earth, scientists could basically create an X-ray of its hidden structure.
And once they figured this out, the discoveries started rolling in. First up, Andrija Mohorovičić noticed that earthquake waves would suddenly change speed at a specific depth, revealing a boundary. Not long after, Richard Dixon Oldham used that same data to find an even deeper layer, the Earth's core. And finally, Inge Lehmann put the finishing touch on it, proving the core itself has a liquid outer section and a solid inner part. A whole new map of our world was taking shape.
All right, so let's peel back that first layer. This is the one we know best, the crust. You can think of it like the eggshell of our planet. It's thin, it's brittle, and it's broken into pieces. And pay attention to this part. Notice how it's much thinner under the oceans. That is a super important clue we'll come back to.
Okay, go deeper. And you hit the mantle. And this isn't just another solid layer. Oh no, this is a vast, superheated ocean of partially molten rock we call magma. And it's constantly, slowly churning and flowing. The heat here is immense, and all that movement is basically the engine that drives everything on the surface.
And then, right at the heart of it all, you get to the core. It's a ball of incredibly dense iron and nickel, with a liquid outer layer surrounding a solid inner core that's being squeezed by just unimaginable pressure. And the temperature? Get this, it's nearly 6,000 degrees Celsius, which is as hot as the surface of the sun.
So, figuring out these layers was a massive step forward. But you know how science is. Solving one mystery just opens up another, even bigger one. Scientists kept finding these identical fossils of land animals on continents that were separated by thousands of miles of ocean. How in the world did they get there?
For a while, the leading theory was something called land bridges, the idea that ancient strips of land connected everything, and then just sank. It kind of made sense. But then, in 1912, a geographer named Alfred Wegener came along with a totally wild, radical idea. He said it wasn't a bridge that disappeared, the continents themselves had actually moved.
I mean, Wegener did what a lot of us do. He looked at a world map and saw that the continents looked like they fit together, like pieces of a giant jigsaw puzzle. He called this original supercontinent Pangaea. His idea was brilliant, but, and this is a big but, for decades nobody took him seriously. Why? Because no one could answer the big question. What force on Earth is powerful enough to move an entire continent?
So what was that force? The answer wasn't on the continents at all. It was deep below them, in the immense, churning heat of the mantle we just talked about. The process is called a convection current, and honestly, the best way to picture it is like a pot of boiling water. Magma gets heated by the core, it rises up, spreads out sideways right under the crust, and then sinks as it cools. This slow, circular motion creates a massive conveyor belt that literally drags the plates on the crust along with it. Wegener's crazy idea finally had its engine.
So how fast is this conveyor belt moving? Well, on average, about 5 centimeters a year. That doesn't sound like much, but get this. It's roughly the same speed your fingernails grow. Over millions and millions of years, that slow, steady crawl is more than enough to move continents clear across the globe.
Okay, so we've got these giant plates constantly cruising around. It's only a matter of time before they run into each other, right? And when they do, well, that's where some of the most dramatic stuff on Earth happens. We call this a destructive margin.
Think of it like a heavyweight versus a lightweight fight. When a dense, heavy oceanic plate smacks into a lighter continental plate, the oceanic plate always loses. It gets forced to dive down into the mantle. This whole process is called subduction, and it's basically how the Earth recycles its old crust.
And the consequences of this are just immense. The plate bending down creates these incredibly deep ocean trenches, like the Mariana Trench. At the same time, the edge that's sinking melts back into magma, which then fuels these really powerful, explosive volcanoes on the surface. The sheer weight of that sinking plate even helps pull the rest of the plate along, a force we call slab pull.
But plates don't just collide, they also pull apart. This happens at what's called a constructive margin, and it's called constructive for a good reason. Instead of destroying crust, this process actually creates it.
It's pretty straightforward, really. As two plates separate, a gap opens up. Magma from the mantle just rises to fill that void. Then it cools and solidifies to form brand new crust. It's like the Earth is constantly healing itself and building new ground from these seams. This process creates these massive underwater mountain ranges called ridges, like the Mid-Atlantic Ridge. The volcanoes here are much gentler, kind of shield-shaped. And sometimes this rifting can happen on land, literally tearing continents apart. That's exactly what's happening right now in Iceland and in Africa's Great Rift Valley.
Okay, so let's do a quick recap. We've got destructive margins, where plates move towards each other, creating volcanoes and deep trenches. We've got constructive margins, where they pull away from each other, making new crust. And finally, we have conservative margins. This is where plates just slide past one another. They don't create or destroy anything, but when they get stuck, they build up incredible pressure that eventually gets released as a powerful earthquake, like along California's San Andreas Faults.
And that really brings us to the main point. The ground beneath our feet is not solid and unchanging. It is the skin of a dynamic, living planet. Powered by the incredible heat of its core, the Earth is constantly destroying, creating, and rearranging its own surface in a cycle that's been going on for billions of years.
And that process is still happening right now. The Great Rift Valley is slowly tearing Africa in two. Scientists think that in about 10 million years, a whole new ocean will form right where there's land today. It really makes you wonder, what other huge changes are already underway, and what will the map of our world even look like millions of years from now?